Hi, everyone. Thank you for attending my talk. Today I'm going to talk about system design considerations for next generation frontier models, as well as current generation ones, and a bit of an overview about training and inference generally. I'm Dylan Patel from SemiAnalysis. So first thing I want to discuss is just what are frontier models, right? And the best way to measure them is just the raw amount of flops that are delivered to them. So there's some estimates up here because not all models are publicly known on how many parameters, how many tokens, et cetera. But our estimate of GPT-4 is that it's about 208 billion active parameters, 1.8 trillion parameters total. Active meaning how many are activated per forward pass. And so to train it required roughly 2 E25 flops, or floating point operations, not sec per second. And since then, there have been some models that have come out larger, but we sort of have a waiting period as these massive H100 systems have been built for the next generation of frontier models, right? And that's highlighted by that orange circle there, right? These models that are an order of magnitude larger than GPT-4. And so these models, well, what are they going to require, right? Or what are they going to be, right? They're going to be an order of magnitude more flops. They're going to be trillions of tokens, tens of trillions of tokens, and have a lot of multimodality, right? Because text only is sort of running out. Image, video, audio is sort of the path to get more data. So over the near term, right? Today, people are targeting 10E26 to 10E27 models. If you discuss systems out 3 years, 4 years from now, and if you talk to some of these AI companies, they want orders of magnitude larger than that, right? And they will seriously, soberly say $100 billion systems, which is quite incredible. Hard to believe, but that's what they want to do, right? And so what are the general requirements here, right? There's sort of two general parts of the model, right? There's prefill, decode. So prefill is when you are processing the prompt. And so that is a very compute-intensive portion of running a model and serving it. And so generally, the GPT-4, the estimated size that we indicated, would require 20 petaflops just to process 32,000 tokens, right? In its prefill, right? So when you send a prompt that is 32,000 tokens long, it would require roughly 20 petaflops, which is an incredible amount of compute. It also requires a lot of memory capacity for that prompt, the KV cache, but it doesn't actually require much memory bandwidth or really anything else. On the flip side, there's decode, right? And this is, okay, you've processed the prompt, now let's iteratively generate the tokens. This requires a stupendous amount of memory bandwidth, not necessarily compute, right? So generally, you might consider, hey, I'll send a prompt that is 32,000 tokens, right? Maybe that's like 20,000. That's like 30, 40,000 words, and you'll get an output of a few thousand tokens back, right? So that'll end up being a huge amount of compute upfront in the prefill, but then the decode, every single time you generate a new token, you must load the whole model into the chip from memory, and then compute, and then continue to iterate that, right? I mentioned GPT-4, like 1.8 trillion parameters. There's no chip today, no chip tomorrow, no chip 3 years from now that's going to have enough memory to satisfy that, right? And the memory bandwidth required, right? Because, hey, if you want to use a model, you don't want to wait all day. So what's an acceptable rate? A lot of people have settled around 30 tokens per second. And so 30 tokens per second would mean you'd have to load the whole model in 30 times per second, 1.8 trillion parameters, which means over 50 gigabytes a second, or terabytes a second of memory bandwidth. Impossible for a chip to have, right? So this is really about a system. And so, if you're serving 64 users concurrently, 30 tokens per second, that's only a petaflop of compute, right? For 64 users. Whereas what I mentioned prior was 10 petaflops for a single user if they want to do a 32,000 token prompt. So there is a huge lopsidedness in memory bandwidth versus compute on just running a model. And so the system for that has to be very intelligently decided to balance these different requirements. On the training side, right? I mentioned we're waiting for that next generation frontier model. But what is GPT-4? Roughly 20,000 A100s, right? For 90 to 100 days. Over 10 terawatts of power, right? And that was a stupendous thing to do for OpenAI in 2022. No one believed that made any sense, right? But they did it, and it delivered something incredible. Now we'll see what the quote unquote 100,000 GPU system that they're making today will deliver. But if they wanted to redo GPT-4 with that large of a system, it would only take roughly 3 days. So it's crazy how much additional compute is being delivered. And so the next sort of thing I would like to discuss is what's going on, right? I mentioned this huge memory bandwidth requirement in decode, a huge compute requirement during prefill, but the chips have done something very different, right? They can't really abide by what models want. They have to abide by the laws of physics. And the laws of physics indicate that memory is progressing much slower than digital logic, right? So we've seen a huge increase in flops for NVIDIA's GPUs, A100, V100, H100, and then GB200, same thing, right? The flops increase way more than the memory bandwidth. And the other interesting thing to think about is it's not just flops, right? So this is, I believe, GPT-3 in the bottom right, the proportions of operator classes in PyTorch. But while over 99.8% of the operations are matrix multiplies, it's only 16% of the runtime. Other way to look at it is, hey, this 0.2% of operations is actually 40% of runtime, right? These statistical normalizations, these element-wise operations. So it's not just, AI is not just, hey, big matrix multiplies, right? A lot of people try to pitch that. I mean, it is, that's table stakes, but there's a lot more going on, a lot more complicated. The other thing, again, going back to the memory wall, right? Memory has just not been decreasing in cost. And if I were to update this chart a little bit nearer, it's actually going up, unfortunately. But this is really challenging because these models require, if we're talking about next generation models, right? GPT-3, 175 billion parameters, GPT-4, 1.8 trillion. What is GPT-5? I mean, let's just be stupid and say it's 10x, right? It's 10 trillion plus parameters, right? That's going to require a ton of HBM. And that cost and performance of operating that model's inference, serving it in an economic capacity, right, is going to be gated by memory capacity and bandwidth, not necessarily just advanced logic. Now, of course, the best companies in the world are going to push to 3 nanometer and beyond. They're going to push to the most leading edge logic. But really, the memory is a real big challenge for them. And so I'll hit on that point just a little bit harder, right? If you're talking about achieving real-time user interactivity, right? 30 tokens per second, something reasonable. A lot of people argue you want faster than that, right? Companies like Grok argue you need hundreds of tokens per second per user. But if you look at ChatGPT today, it's about 30. That's 50 terabytes a second, 54 terabytes for just loading the parameters, ignoring KV cache, ignoring the activations, right? That's the middle states of the model as you're processing it. So just the parameters is 54 terabytes a second of memory bandwidth. You can see that there's no real system capable of achieving high throughput on a single chip, right? For a model so large. And so that's sort of what and this is at about 50% utilization for the memory bandwidth. It's kind of tough to get really high utilization. People get like 70, 80, but it's effectively impossible. So you have to use multiple servers, not just one server, not just one chip, but multiple servers. So three to four H100 servers, 8 GPUs each. Each of those costing like $300,000, right? This is very expensive stuff. So what are modern systems capable of, right? This is the price per GPU, right? $24,000 for H100, H200. B100 is about 30, and GB200 is in that $36,000 range, right? 36 to 40. And the power consumption goes up, the flops go up. But you can notice the memory bandwidth does not go up near as much as the flops do, right? Especially if we're talking about low precision, which everyone is rushing to, right? The microscaling formats, right? MX8, MX4, et cetera. So modern systems are capable of a lot, but one chip is not enough, right? So reiterating, what is this next generation model, right? If we again go stupid, it's just 10x the 1.8 trillion parameters, roughly 20 trillion parameters, right? What is the training flops, right? 2E25 for GPT-4, again, roughly 10x. It's in that 10E26 to 10E27 range. What does that mean? It means you need 100,000 GPUs to train that, and to inference that model, you would need 200 terabytes a second of memory bandwidth at high utilization with a 4-bit floating point format, right? Or integer format, either one, right? But it would require over 200 terabytes a second of memory bandwidth just to serve that model at human usable speeds, right? So what does that system look like, right? The GB200 is 72 GPUs in a rack. It's a multi-million-dollar rack that NVIDIA wants to sell. Everyone's like begrudgingly buying it. Why are they begrudgingly buying this humongous system, effectively a mainframe, right? When for the history of the last 20 years of servers has been commodity parts and a lot of them, right? So why are people doing that? Because you need the 576 terabytes of memory bandwidth that it delivers in a single rack. And if we're talking about, in the future, things keep scaling, it's going to continue to get even crazier, right? And that has to be delivered just to serve a single model, right? Now you can serve multiple users, but there's a massive challenge in continuing to scale because we already broke past the bounds of a single chip. We already broke past the bounds of a single server, right? Now we're in the next generation systems, next year people are going to be running into how do we break past the bounds of a single rack, right, at extremely high bandwidth via NVLink, and competitors will have similar things. And then likewise, like I mentioned, right, these companies who are at the forefront today, OpenAI, Anthropic, Google DeepMind, right, they talk about not just 100,000 chip systems, right, which is what they're building / training on today, and will release in the upcoming 6 months, year, et cetera. But also, they're talking about gigawatt scale clusters, right? Hundreds of thousands, million chips, right? And what does that mean for serving that model, right? Because maybe you can convince someone to let you train it, but how are you actually going to serve it? So these next generation models are going to push the limits of everything: silicon, interconnect, systems, and power, right? And so what does that mean, right? So today this is a satellite image of Arizona for Microsoft, right? So this is 3 data centers that they've tied together to train a model, right? This is the third data center is actually in construction, but it's like a few months old picture. It's actually complete now. But that's, each of those buildings is 48 megawatts, roughly 150 megawatts total for all 3, right? And they have to interconnect multiple buildings, right? It's not the same as just like, hey, we can use optics connect servers in a rack or between racks. No, we're going between buildings. These are miles of interconnect, right? Hundreds of miles in aggregate fiber just for one, training cluster. This system cost over $125 million a year to run, just in electricity, right? And in fact, this is with I think we used 5 cents a kilowatt hour. I don't think anyone here pays 5 cents. I think if you live here, you pay like 30, but it's $125 million a year just to run this system. And to build it costs north of 5, right, billion. So it's a humongous capital expenditure that's been made. And these models will come, but when you look at say for example Elon Musk, right? Elon Musk is tweeting about, yeah, we've already got our 100,000 GPU system being built in the next 3 months for his XAI, right? And he's saying next year we're going to build a 300,000 GPU system. So if that's the case, right, then that's because those GPUs are much more expensive, right? They're much more higher power, right? And there's more of them. That's going to consume 600 megawatts, not 150, right? And that's going to cost $400 million a year to operate. Again, at 5 cents a kilowatt hour. 8.7. That's an incredible amount of money, but hey, he just raised $10 billion. So we'll see. It's going to happen, it seems like. And to interconnect these clusters is not just, hey, we run fiber between buildings on the same campus. It's very difficult to get that amount of power in one location. So in fact, you're actually going to end up with running, you're going to need to interconnect campuses within the same region. Again, so not just a server, not just a rack, not just a data center, not just 3 data centers. It's many data centers in an entire region, right? This is the plan of XAI, OpenAI, et cetera, and they're working with companies like Microsoft and Amazon and Google, et cetera, are building these systems, right? So the power requirements are ridiculous. They're scaling beyond a single data center, right? So Jeff Dean gave a talk a couple months ago, but it was very, very interesting. I'll give you the synopsis of it. Jeff Dean leads a lot of AI things at Google for a simple, high-level view of who he is. And he was talking about this exact problem, right? Hey, we can run, an AI in just one data center or one campus. And there's different kinds of optics that we need between them, right? There's multi-mode optics, there's single-mode optics. But actually, you're going to start to need to go between campuses. That's going to require very expensive coherent or coherent light optics. So there's a lot of companies that are working on that, like Marvell and AlphaWave and such. You'll have all these pods of compute that you're interconnecting across tens of miles, right? Not just a few miles like the prior systems that I showed, but tens of miles of fiber, and the bandwidth between each domain is going to be lower, right? If I'm within a rack, then I have my NVLink if I'm NVIDIA, I have ICI if I'm Google. Everyone's going to have their flavor of that. UA Link if you're part of the broader ecosystem. AMD and many others are adopting UA Link, right? You'll have that within the rack. You'll have Ultra Ethernet, connecting many racks together. And of course, Ethernet will connect these data centers together, but it's a different type of pipe, right? It's not quite as much bandwidth. It's not all-to-all bandwidth. So there's a lot of considerations on designing that system. Networking is a huge consideration. Also, one important thing to think about is the cost of networking scales exponentially with cluster size, right? So when you go from 8 GPUs to 16 GPUs, your network cost is very tiny. When you go to 16,000 GPUs to 32,000 GPUs, your networking cost becomes something like 15% if you're doing an all-to-all network. But if you're going from 32,000 GPUs to Elon's 300,000 that he wants to build next year, and I'm sure OpenAI and Anthropic and others will do similar, then your network costs are going to approach 30-40% of the cost of the system. So there's a significant amount of work that needs to be done on the network side, which is important to consider. The other thing that's really incredible is if we think about, like, a lot of people here are design people, what's the bit error rate that you're okay with, right? I've heard from a lot of people 1E minus 18 is like a good bit error rate, right? But remember when I went back to the beginning of the presentation, it was 2E25 flops to train it. So how much data are you moving, right? So 1E minus 18 means you're still throwing a lot of errors, right? And even with ECC, even with all of these things to prevent faults, bit flips, et cetera, you're going to have a lot of bit flips, right? So optics are one of those things that are notoriously unreliable. HBM ECC is also relatively unreliable, right? You end up with a lot of failures. So as the size of the cluster grows, you're going to have soaring failure rates, right? So for example, right, even if you say optics last 10 years, right, then the mean time to failure for an optic is extremely high. And I think most people know that high-speed optics, right, 400G, 800G optics do not last 10 years, right? So in reality, it's probably more like 5 years. So if you're at 10,000 GPUs, then you're failing, not too often, right? Every 262 minutes, right? So every few hours you have an optic fail. Not a horrendous thing, right? You can deal with that. But that's at 10,000 GPUs. Let's scale up to 100,000 GPUs, right? That's the systems that people are deploying this year, right? XAI, OpenAI, et cetera, right? And those systems, if you have that 5-year failure rate, your optics are failing less than every 30 minutes, right? Means you've got to figure out how to route around in this network every 30 minutes. If your training run fails because an optic failed, right, then you need to restart the whole training run. So you need to build many fault-tolerant strategies to either restart and resume training runs quickly, route around failures, and this is something that is a tremendously difficult task, right? Rocky, InfiniBand, those links fail, the transceivers fail constantly, right? And that's just one example. Actually, more than half of all failures are just related to HBM ECC not working properly, right? As in, it just didn't catch the error on these massive clusters, right? That's a statistic that people at these large companies will just say, but they won't actually give you data. So I'm not 100% sure, but they say more than half their failures are related to HBM ECC, right? And again, 100,000 GPUs. Each GPU is 3 terabytes a second of memory bandwidth. What's your bit error rate, right? That's pretty, and ECC will not catch them all. So how do you deal with these faults is incredibly difficult. And you have to live with the faults. You can't just live in a world where, hey, you will have faults, or you can reduce the rate of faults. You actually just have to figure out how to deal with them. The other thing is stragglers, right? A lot of people here probably know about the silicon lottery, right? Which is, the curve of, hey, when you manufacture a chip, some of them are really great, some of them are really bad, right? And there's a humongous range. And even when you get sold, say, an i7, right, or a H100, there is a range of performance, right? If it's power limited, for example, you might get 5 or 10% more performance out of one chip than another. It's just what happens. It requires slightly less voltage, or clock speeds end up being slightly higher in the same power budget. And so if only one chip in that 500,000 GPU cluster, right, is 10% slower, then the entire cluster is slower. Same applies for smaller clusters, but the variance is smaller because you have a larger cluster, right? So the straggle, because training an AI is a synchronous task, right? Everyone does a bunch of work, and then they sync up their weights, and then they do a bunch of work, they sync up their weights, right? So that syncing up of the weights, when that happens, if one person's not done with their job, then everyone's waiting on that one person. So having this curve of performance across chips is actually going to destroy your training performance, right? Because it's not just, hey, this chip is generally 3x faster than the last generation, but if one of them is 20% slower, 10% slower than all the other ones, then that one chip is going to slow down everyone else. And that's, $120 million of electricity every year for that H100 cluster. Well, if it's 20% slower, 10% slower, then you can do the math. That's tens of millions of dollars in just electricity you're burning, let alone the capex of billions. So a holistic analysis needs to be done even once a company gets the chips, right? When you're manufacturing, you're going to do probing, you're going to do system level test. But once it gets delivered to the customer, they also need to do system level analysis and actually just remove GPUs that are slower, even though they're completely functional. So that's something that people do is like, oh, this node is just slow. Well, we'll throw it to like inference instead of like in this massive training run. So people do that. And ByteDance, there's a paper that they have that showed they have a 25% decrease due to these stragglers, right? This slow GPU. So dealing with that, dealing with reliability, right? Fault tolerance, dealing with making all chips perform the same is very, very important as well, right? Otherwise, you're going to lose performance. HBM, right? Going back to the memory wall that I discussed earlier, right? There's a lot of work going on at HBM4 for custom HBM, right? So today, your H100 has 6 packages of HBM. MI300, B100, they have 8 packages of HBM per chip. Systems are obviously going to require larger packages, and there's a lot of advanced packaging work being done to grow that ratio. A lot of new forms of packaging, panel level packaging, or system on wafer fan outs, and all sorts of other stuff that people are doing. But one of the really, really interesting things that people are working on today is custom HBM, right? So Micron's working on this, SK Hynix is working on this, Samsung's working on this. They've all talked about it to some degree, but they haven't described what exactly this means, right? I mentioned that HBM speeds are growing much slower than flops, right? And all the way from NVIDIA's V100, every generation that's been the case, up to the B100. Same will apply to AMD's AI chips, Google's TPUs. Every generation, the flops grow much faster than bandwidth, but the models necessarily don't want that. So one idea that people have had, that people are working towards, is putting, HBM, right? There's many layers of HBM, and then on the bottom of that is a base tile that does phi, right? It connects, it does the physical layer between the two systems, right? The logic and the HBM. One of the ideas that people have is, what if we make it so you can actually repeat the signal and you can have 2 stacks of HBM, behind each other, right? Instead of one right next to the logic, right? So that's one idea. Another idea is, well, what if we put LPDDR behind the HBM, right? The HBM base tile has a memory controller for LPDDR. Another idea that people have had is, what if we just put the memory controller for the HBM on there, so then there's more compute on the main logic silicon. So there's a lot of ideas being worked around, but the clear goal is that multiple AI chip companies are working on custom HBM base tiles with various different elements inside the HBM, right? HBM is not a commodity standardized product in the future, right? It's a JEDEC standard today, right? And JEDEC gets to set the standard, but that's not going to be the case going forward. If you have enough volume, you will integrate more capabilities into your HBM die that might be only single source, or rather, a company like NVIDIA or AMD or what have you will make the HBM-based die and give it to all the memory makers and have them package it together. So there will be less of a commodity market, right? And DRAM has generally been viewed as a commodity, but that's not the case going forward with custom HBM. Another thing is interconnects, right? So when we look at interconnects today, people are using 112G or even 224G, right? If we look at 3 nanometer high-speed SerDes tapeouts, I think there's like 8 companies that have done high-speed SerDes tapeouts, right? There's a lot of people here selling SerDes, Cadence, Synopsys, AlphaWave, and so many more companies have. Sorry if I didn't name your company if you're made one, but I've tracked about 8 companies have made 3 nanometer high-speed SerDes, right? That's incredible, because in the past, when you looked at 5 years ago, there was only a few companies that were had high-speed SerDes. And now all these companies are trying to make them. Doesn't necessarily mean they'll be successful, but that kind of points to why, right? Why? Because the demand for them is so voracious. High-speed chip-to-chip interconnects are needed, right? I mentioned models don't fit on a chip. They don't fit on a rack, right? They fit on multiple racks now, or they will. And so you're going to need extremely fast SerDes. And so protocols like NVLink and now UALink are the future, right? And even further out, people are going to these co-packaged optics, optical interposers, glass substrates, et cetera. There's a huge amount of work being done to combat that memory wall, right? That serving a single model inside a single rack is the next generation system, but beyond that, serving a single model inside of what system? And that's on the scale-up side, right? Which is generally the NVLink, Infinity Fabric, UALink, ICI, that sort of domain. When you go to scale out, right, which is sort of Ethernet, that's connecting hundreds of chips together, thousands of chips together, right? You need very high radix switches. So you have Ultra Ethernet, you have all the packet, you have the packet spraying, and all these things that Ultra Ethernet is working on. Of course, NVIDIA has their InfiniBand stuff. There's thousands or millions of accelerators in a single training run. There's multiple companies working on optical circuit switches. If you've seen Google's optical circuit switch, which they use in their AI systems today, right? It's not an electrical switch, it's an optical switch. And then you're going to need these coherent optics, right? ZR Plus and such to connect between data centers. But these high-speed interconnects are extremely crucial because the model has to be split across, right? And so what's, a lot of people have been talking about CXL, but CXL is dead in AI, right? CXL just does not work. There's many protocol things that make CXL not work for AI, but really it's as simple as, you can have that discussion, but it's really, what is the speed, right? And the speed of CXL is just far too slow for AI. Today people are PCIe Gen 5 and they're going to Gen 6. And even when they go to Gen 7, that's 128 gigatransfers per second. NVIDIA's GB200 that they announced and is shipping in Q3 or Q4 is 224G SerDes, right? So it's twice the speed of PCIe 7, which is next year, right? And who's actually going to have a system with PCIe 7 next year? So PCIe SerDes are far too slow, right? Which is why UALink even came out, right? Because CXL could have been the interconnect for AI, right? The open interconnect that everyone used, but it can't be because it's too slow. Again, ignoring the protocol issues that it has for specifically accelerator communications. And so the PCIe Gen 7, right, 128G SerDes, those are being leapfrogged into UALink, right? And then beyond that, UALink will have 224G SerDes. You need to go much faster than the CXL roadmap is, which is why no one is adopting really CXL in their AI accelerators, right? If you're NVIDIA, you're using NVLink, and if you're everyone else, you're going to have to adopt UALink, right? This new consortium that AMD sort of really started up with a lot of the hyperscalers. So CXL is far too slow, and it's kind of dead in AI, at least, right? It'll be fine for memory pooling of CPUs, but that's not the workload that everyone is so excited for and throwing money at, right? And then sort of the last thing I wanted to talk about is just these future inference requirements, right? So I mentioned a 2,000 length prompt, right? 2,000 context length prompt would require 10 petaflops, right? That 32,000 length prompt will require 160 petaflops. This is very compute intensive, of course, right? Hundreds of accelerators will need to be used for prefill, right? Computing that prompt before you even start serving the user. But even, with NVLink or UA-Link or what have you, right? The other thing is to serve these 64 users, 64 users concurrently, which seems like a reasonable thing to do on a system. This theoretical next generation model, that's going to be 600 terabytes a second of memory bandwidth, but only 10 petaflops of compute, right? For 64 users, which is a extremely low amount of compute. Again, so there's a couple different things that people are doing here, right? Because these workloads are so different, prefill and decode, there are strategies to actually split them apart. Today, people split them apart on the same chip, not the same chip, but on the same type of chip, right? So you'll have nodes dedicated to prefill, you have nodes dedicated to decode, right? But they'll just be H100s, frankly, right? Or they'll be TPUs, right? Google does this at scale, and many other GPU-using companies also do it at scale, right? Is splitting the prefill away from the decode. It also lets you have better, servicing of the customer. But one thing that a lot of people are, contemplating working on is, do you actually just make separate chips for this, right? Do you make a separate chip for prefill? Do you make a separate chip for decode, right? Sure, an AI accelerator is great. Sure, a training versus inference AI accelerator is great. But really, in inference, there's two different workloads. So do you need two different accelerators for that? Now that's, good luck convincing your boss to spend that much money on a tape out and design. But there is a reasonable argument that you do need two different chips for serving large language models and multimodal models, because the compute heaviness of the prefill versus the bandwidth heaviness of the decode, even when you are serving many users concurrently. So there's a lot of challenges with these future systems. Huge amounts of compute, huge amounts of bandwidth. Interconnects need to be stellar, and then when you scale to really large systems, really worrying about reliability, fault tolerance, et cetera. But that's about my talk. But I can answer some questions. The two mics are open. Prefill is processing the prompt. So you have to compute the KV, the attention, the KV cache, et cetera, when you receive the prompt, and then you can actually run it through the model.
Excellent talk, highly educational. What I wanted to find out was, this is for initial training, right? If you were to assume very few people will be able to, build this kind of infrastructure to do training of new models with larger number of parameters, what are your thoughts on retraining, taking trained models, and what kind of compute and memory bandwidth requirements are needed there?
Yeah, so I talked about two topics here, right? Training of these massive models, which does require these hundreds of thousands of GPU systems, but also inference, right, which requires these smaller systems. But still very large systems, rack scale, right? If you want to fine-tune models, if you want to take models that already exist and improve them, you don't need to retrain the whole thing, right? Far less training compute, but the system still has to look the same, right? It still has to be able to run the model across many, many chips, right? Now, you don't have to replicate it across 100,000, maybe you only have to replicate it across a few thousand. But you still need, all of, the chip-to-chip interconnect, right? And more than just fine-tuning, right? The inference side is going to require all these things, right? So even if you don't train the model at all, right? If you just have a model and you want to run it, that requires all this memory bandwidth, that requires all this compute, right? And that's sort of what this last slide is touching on, is to process a single prompt is 160 petaflops, right? Or But whereas to run even to serve 64 users is significantly fewer petaflops, but it's far more memory bandwidth, right? So the systems for them, for those fine-tuning models, are gonna look more similar to maybe the inference systems. They're not gonna look like those 100,000 plus GPU training systems, but you're gonna need to be able to serve that model everywhere, not just one company serving that model.
Thank you. Thank you.
Hey, Dylan. Good morning. Just a clarification question. You said CXL is dead in the context
Of AI.
of AI. not completely.
Correct. CXL is great for CPU to CPU, memory pooling, right? Memory sharing, memory expansion. That's great, but for accelerators, it's not the go, right? Because you're extremely limited on edge area of the chip, right? You only have so much edge area, and you're not going to dedicate it to a very slow interconnect. That also has protocol problems when connecting to accelerator. You're going to have to use, things like UA link, NV link, and then in the scale up domain, right, which is where CXL is playing, and then in the scale out domain, you'd be using Ultra Ethernet. There's no room for very slow CXL 3.0, which no one has even shipped a product yet with, but even CXL 3.0 is too slow for AI on a pure edge area, right? If you were to put CXL on the GB200 instead of NVLink, your bandwidth would be about 1/3 of what it is, right? Their total NVLink bandwidth, right? If they just replaced NVLink with CXL, very just based on the SerDes speed, right? Because they are edge limited. So you can't afford to make that trade-off in AI, but CPUs are obviously going to be a very PCI heavy workload, care more about latency than they do bandwidth, and so CXL has room there for memory pooling and things like that.
And a similar question on the building-to-building connectivity to talk about all the protocols there for allowing this?
Yeah, so those are still going to be Ethernet, right? I mean, that's how, when I talk to you, it goes to, if I were to text you through, say, or email you, it'd go through Google servers, right, on Ethernet, and all across the world on Ethernet. So it'd still be Ethernet, but it would have to be, it's not just about the protocol, it's about the, there's going to have to be routers, right? And today, you look at these humongous routers that people build from, whether it be Arista routers or Juniper routers or Cisco routers. People don't use those in AI today, though, right? So they're going to have to figure out how to integrate these routers into data center to data center communications for training AI, and they're going to have to use a whole different class of optics, right? Not standard EMLs or VCSELs or what have you based lasers, but they're going to have to use tunable lasers with coherent optics. Very, very expensive telecom stuff, and they're going to have to figure out how to integrate that. But the protocol itself will still be Ethernet.
Thank you.
Very good talk. Now, so I have one question is, you already
Can you step a little closer to the...
Oh, sorry, yeah. Very nice talk. And you already summarized the training and the inference, but in a system, there's storage and a network. And so your computing unit need to connect with the storage and network. Any thoughts on this side? Any change?
Sure, absolutely. So I talked a lot about the scale up and scale out networks, right? The NVLink / UA link between, call it 100 accelerators and Ultra Ethernet or maybe InfiniBand across thousands of GPUs or tens of thousands. But there's actually 3 networks in any modern AI system, right? There is the scale up domain, right? Low latency, more maybe coherent between a small number of accelerators, right? Today it's 8 GPUs. And then there's Ethernet connecting all the GPUs to each other on the back end, but there's also a front end fabric, right? And that front end fabric, generally it's just today most people do either 100G or 200G NIC in a server and connect it to high speed storage. The storage world will have to evolve, right? There's a lot of investment going on, but I'm just not as well versed in that world. But also generally an AI system, at least empirically, the cost / money spent on an AI system in storage is significantly less than a standard CPU storage system, whereas networking and accelerator spend obviously soar. So that would at least indicate that the problems in storage are maybe not as large as the problems elsewhere. But of course, there's going to be problems in storage when you scale to systems this large.
So very good talk on the state of art and how we got here. But I would think we should take a step back and see that there is a lot of brute force compute being applied to a lot of data. I have to think when the 80-20 rule would still apply, that 20% of training data has 80% importance for the weights in a neural network. So if we can somehow go and look at the training data that we are feeding these machines, that's one thing. And second thing is, just like in a chip design, people use hierarchy and cell libraries and stuff like that. in a model, instead of thinking of that as a flat model that needs to be trained, look at it incrementally, like Duke asked about incremental training in the field. If you can see which weights would change because of some input data changing and only go and do that part of retraining, I think a lot of software and algorithmic intelligence is needed instead of throwing this lot of brute force power and transistors at the problem.
I think we'll scale across all vectors, right? Data is absolutely important, but when you think about what was GPT-4 trained on, right? 13 trillion tokens. That is so many words that even 1,000 humans could not read them in their whole lifetimes if they read the whole time. It's so much training data. We're not looking at the training data. We're kind of making some heuristics on what to remove, but in reality, there's no way to actually. It's just okay, let's take the whole internet and train it, right? Remove some of the naughty stuff. That's basically all we can really do, and that's the approach. Now, of course, that's way less efficient than curating your data set manually, but if you curated your data set manually, no one is getting anywhere close to this level of intelligence, right? The other thing is, the argument you hear a lot from AI researchers is, well, the human brain has about 100 trillion synapses, right? Connections in the brain. So if you think of a parameter as a synapse, then we're nowhere close to even the human brain, right? Biology is beautiful, and we're nowhere close to that. But we do brute force it by throwing a whole lot more data, which is why you kind of get sparks of intelligence, but maybe not as much as a human would be if they were really dedicated to a task. So you kind of get that argument there too, which is one, when you train a human, you curate the data set as best you can, right? You send them to a great school and what have you, but that doesn't really. You don't know the end result, right? And the only hope is for a child with this 100 trillion synapses is they learn a lot and they become successful and they become a good person. And it seems to me that the AI researchers are treating this the same way. Let's just throw everything at it. Let's curate the bad things out, and maybe that'll make something that's super intelligent. Because today the system where they throw everything at it, brute force, is more intelligent than any other system that we've ever built. It's not human level, but it's certainly very intelligent. Yes, there will be algorithmic improvements, right? People are doing mixture of expert models and more sparse models generally. People are adding more data, but they're going to curate data, but you can't possibly. I mean, if someone can replicate the results at a much smaller scale, that would completely change the world. But today, the results speak for themselves, and the only thing that people do know is that the scaling laws exist, which is from 2017, 2018 for transformers. Every order of magnitude of compute has delivered improvements in the benchmarks, whatever those benchmarks are, right? So we'll see if that continues to happen, but they're called scaling laws. They're not laws of physics, but actually Sam Altman called them a law of physics at a talk at Intel's Foundry event, actually, earlier this year or late last year. But yeah, we'll see what happens. But certainly that seems to be the most promising vector of scaling. There will be algorithmic improvements, there will be data improvements, but throwing more compute is clearly very successful and has generated a multi-billion-dollar business, maybe multi-tens of billions of dollars of business for Microsoft.
Yeah, it is until it is not, right? I mean, so one thing with intelligent computing is if you look at nature, that's one of the best computers out there with evolution. So about 90% of DNA information is junk, right? It's only few small percentage difference.
But we still don't know which percentage is useful in many cases, right? And the same applies for the brain, right? We don't know what percentage is useful, this massive, massive machine, but we don't understand it. And I would argue we don't understand how LLMs work really either.
Thank you.
Yeah.
Excellent talk. The question that I have about is benchmarks. Obviously, there are existing benchmarks like MLPerf and stuff like that out there, but they're not really quite designed to kind of address some of these scale kind of problems that you're talking about. So I'm kind of curious about your thoughts on what should future benchmarks be like, and what are the problems that we have today to make intelligent decisions, really? Yeah, so on the performance side of things, it's really difficult, right? MLPerf this year, I believe, added, or last year they added GPT-3 training. Like 3 or 4 years after it was released. I mean, it's an industry body. They're doing the best they can. They added Llama inference this year, right? Llama 70B. Great benchmarks that people absolutely need to measure and are way more accurate than measuring the performance of BERT, right? But
yeah, like that doesn't tell you actually what does even GPT-4 look like, right? Training that. And that was the problem 2 years ago, right? 2022 when they made it and then released it in early 2023, right? So what's the problem of today? One, I find it hard to believe that people are going to build these $10 billion systems and just tell everyone, this is what you need to run, right? Because then their competitors would know, they'd be able to replicate it maybe, what have you, right? So it is tough to figure out what the exact benchmark is, right? The nice thing is that there's many layers of the abstraction stack, like always, and so people can always optimize and engineer for their layer of the abstraction stack, but a holistic, even GPT-3 training, right? MLPerf has constraints, right? Who's going to run a benchmark and cost millions of dollars, right? Or even hundreds of thousands of dollars. So MLPerf only does a tiny sliver of GPT-3 training, right? So there's a lot of economic challenges to well, if you're to actually benchmark running GPT-4, then you're going to spend hundreds of millions of dollars, and who's going to benchmark for hundreds of millions of dollars, right? There's got to be some more intelligent way to sell the product, and that just probably ends up being talk to the customer, right? Unfortunately, I don't know what the best benchmark would be, sorry.